Here's the example from tutorial book, chapter 2, question 20, first part. There are 3 parts in that question. All of them identical to each other. I do one, the other 2. It will be a good chance for you to practice these methods. So you're given 2 lines here in vector form. Here they are in front of you. And the job is to find the distance between these 2 lines. Okay? We now have full machinery how to do that, and I'm going to show you these steps. Of course, I expect that you remember our discussion from the last lecture. If you don't, you have to revisit this again after you refresh your views or your thoughts on what we did with you last time. So here's my 2 lines. I will abbreviate the vectors like this. This will be vector A1, the position vector. This will be the vector B1, the directional vector of my first line. Similar notations for the second line, A2 and B2. The formula which we have, which delivers the distance, it just says this. I'll put it here. We just need to compute the length. Let me just put it down a little bit. The formula which we come up with last time is this. We need to compute the length of the projection of what? We have to project onto the jointly perpendicular vector, h, and we have to project the difference between these 2, between the A1 and A2. So here will be A1. Here's a recipe how to find that distance. We have to just follow this recipe. We have to fill in the symbols in this expression and finish the computation. The hardest part here, of course, is joint perpendicular vector, h. And now we have 2 methods of finding that vector in case we're dealing with the 3-dimensional space, with the R3. I showed you one method 2 lectures ago. Oh, yeah, I mean the lecture before the last one. And I will show you the other one based on cross product, the one we discussed with you on Tuesday, right now. Here we go. So when I look for this jointly perpendicular vector, h, as a choice for such a vector, I can choose the cross product of my B1 and B2. Now, cross product, it's a new concept. I think it's a new concept for most of you. I suggest we compute it my computational part of the cross product, it computed the cross product like this. We build this table of 3 times 3, where we fill the first row with the vectors I, j, k, and the other 2 rows we filled with the components of the vectors b1 and the vector b2. Here's the components, 3, 0, 1. These are the components of my b1 vector here. And 3, negative 2, 2. These are the components of second vector b2. Now, then after we wrote the table, we follow this very interesting way of expanding this table into actual numerical vector. And that's how the expansion went. I said first we write the vector I, and next to it we write the table of 2 times 2, which is sitting here. A very convenient way to remembering that is like this. You take the vector I, you cross the row here, you cross the column under I out, and all what is left goes next to the I. Here it is. Similar trick you do with the J, and similar trick you do with the K. That's how we expand the cross product. For the J, again, you take this cross, you center this cross over your J vector, you crossed out the whole first line, I and K, you crossed out the column underneath. What is left? 3. 3 and 1, 2. All of this went into the second 2 times 2 table next to the vector J. And there was a question from the class last time. We have to alternate the signs. Here will be negative. For the vector K, you take this and center over the vector K. You will cross out some rows. You will cross out some columns. The remaining bits, they go into this table. It's a very nice way of remembering how you expand this 3 times 3 table into the 2 times 2 table. I promised you last time that we will go into further details of the determinant discussions, but the computational method, it still will be the same. We will be running this kind of figure across one row or one column, crossing out columns and rows and taking the remaining bits and computing them. So even though we will go further into this discussion, this is already the way it's going to be anyway for the rest of your life, in fact. We're not going to change the way we compute the determinants for the rest of your life, trust me. So each of these individual little 2 times 2 tables, I explain how to compute that. We multiply across the first diagonal and subtract the product across the other diagonal. So if I do that for this vector, that's the kind of result I will have. 2 next to the vector I, because here we got 0, and here we get -2 with extra negative, because we subtract the other diagonal product. -3, because here we got 6, and here we got take 3, that's why it's 3. And for the k vector, here we got -6, and here we got 0, that's why it's -6. As easy as this, right? Even though I showed you this computation for the first time in this class, it took me 2 lines to finish that. Compare this with my solution where we found the joint perpendicular vector via the system of linear equations. It was a longer solution. It doesn't mean it's totally worthless approach. It is a good approach because it works for any dimensions, whereas the cross product works only in 3 dimensions. Yes. So after we have this joint perpendicular vector, my distance here's my projection. That's the same formula I just put here for you. Oh, so it's a long, doesn't matter. I'll take you through this. Here's the projection. For this projection, for the projection onto a vector, we have a very direct, very simple formula. Here it is. I just sub in that formula. If you remember that, it should be easy for you. If you don't, I suggest you revisit that. And then we just cancel one of the h, length of the h, and that's the value for the distance. Structurally, the solution is finished now, because we found the expression for the distance. All we have to do now, we have to sub in the numbers. We have to sub in the numbers, components for this difference. We have to sub in the components for this difference. We have to sub in the length here, and that will be the solution. I guess, let me just check. Yeah, that's all we have to do. I won't be doing this in class. I don't see the point wasting time on this. If you're following my uploads, and in fact, I just see how many people comment what they take off the website. I see that many of you do follow my uploads. You will see the full numerical solution here, which is down here. All of these computations, they will be in the upload. So if you will have any difficulties finishing this computationally, you can take one of those files and finish those. But from the structural point of view, from the conceptual point of view, that's the way we've done it. The equation is done. All we have to do, we have to sub in the numbers and finish the computation. Any questions, please?